Kinetics. You might have heard of it before. Of course, you must have studied it in Gen Chem 2, but I'll give you an example. Pharmacokinetics, there you go. Metabolism, all of this is based on the branch of that's that we call kinetics. And it describes reaction rates. Kinetics is not now interested in how stable the products are to reactants. That's not the question that we ask. We ask these kind of questions. They ask, how fast are reactants converted to products? So how fast is your reaction rate? What is the rate of the reaction and what factors govern the rate? So notice that we do not care. Of course, we care in thermodynamics, but we don't care in kinetics to ask these questions because they're irrelevant. But they're still important, of course, in the holistic picture. A reaction can have a large KEQ, so more products at equilibrium, and a negative delta G, more stable products, but can be extremely slow. It can take days for it to take place. So the rate of the reaction can be defined as the number of reactant molecules converted to product per unit of time. Now, the activation energy is the energy required to overcome the energy barrier to turn reactants into products. So, before we begin, activation energy has this symbol delta EA, or it could be written as this delta G double dagger. So just want you to be aware. But what is activation energy? You might have seen this before. Obviously, we just did it above, but I'm talking about this. Let me just fix it up a little bit here. So if you want to turn A into B, these are your reactants, to be your products. Of course, there's a difference in energy. That's delta H or delta G. But there's also, if you notice that this bump right here, that you go from A to, in order for you to go from A to B, this requires lots of energy. That right here is your activation energy. So you might have thought that A can just simply go like this to B. No, that does not happen. There has to be an increase in energy first. And the reason why is because of a simple reason. Just think about those molecules in solution. When they approach each other, there's going to be an increase in energy because their electron clouds repel each other. So that causes them to move faster, more kinetic energy. There you go. That's what kinetics mean. And that ends up actually raising that barrier. So you need enough energy to overcome this barrier. Don't underestimate this. Again, your reaction rates, metabolism, all of this depends on, again, your activation energy and enzymes. There are two important factors to examine here or to consider. Number one is the size of the energy barrier or the energy of the activation. If the energy barrier is high, a smaller fraction will have of the molecules a sufficient energy to overcome the energy barrier. Here is the equation by Arrhenius equation. The rate constant is related to the energy of the activation. This is K, your rate constant. We have, of course, what we call A as a frequency factor. Basically, it gives you, it expresses the probability that the molecules contain a favorable orientation. When they have a favorable orientation, that means that then they will collide and form a reaction. But what we're interested in here is we're interested in just knowing how activation energy relates to the rate constant. So rate constant, think about it. Here's EA, it's on the top. It's on the top. If you increase EA and you have to the negative power, your reaction rate constant is going to go down, which obviously is seen in those pictures right there. And the opposite is true, is if you bring it down, the reaction rate is going to increase. A good visual is if you decrease the activation energy, the reaction is going to go faster. If you increase EA, the reaction is going to go slower. So let's look at the possible scenarios where you incorporate both the activation energy and delta H, the energy of the reactants or versus the products. So if you look at this example right here, where is EA and where is delta H? So one good way of doing it is the following. Is you draw again so here are your reactants. We're going to call this R right here, and here's our products. We're going to call these P. Is to draw a line right there. EA would be the difference between the peak and the reactants. And delta H would be the difference between the reactants and the products. And in this case, you should be able to tell whether delta H is negative or positive. It should be lower. The products is lower. And remember, products minus reactants. So this should be negative. So delta H is negative. What kind of reaction is this? This should be exothermic. EA, the activation energy, is quite high. Okay, but now we want to actually compare this to that. So let's look at now the other one. Once again, here are your reactants. Here are your products. The difference between these two is EA. And the difference between the products and the reactants is delta H. Now, is delta H positive or negative? It's still negative. So this one is also exothermic. By the way, if you compare the energies of the products and the reactants, they're still the same. We did not change them. Align them, you'll have the same. So something happened here. So we say products and reactants at same energy. And they're both exothermic. My question is, which one do you think would be faster between these two? So we're going to say that this one is low, higher, and lower. Which one do you think would be a faster reaction? One on the right or one on the left? You might have guessed it right. This one would be the reaction that is faster, the faster reaction. So this reaction is faster, and you should explain why. Because EA is what? Is lower, right? So EA is lower. The barrier is lower. Now let's compare. Down here, same thing. This is now A, but you should know what kind of reaction is this. Or this is R and P, I meant. So the difference between the peak and R is the activation energy. And the difference between the reactants and the products would be delta H. So you should be able to tell me whether delta H is positive or negative now. Just subtract them. P is larger than R, so it must be positive, which is, of course, an endothermic reaction. So this is an endothermic reaction. Now let's look at this one. Same thing. This is the difference. Delta H is still positive because the products are larger than they have a higher energy than the reactants. But let's look at their EA. So in this case, which one would be the faster reaction? This one would be the faster reaction, again, because EA is lower. So they're both examples of endothermic reactions, by the way. So you should be able to look at the different ones of the different scenarios and discern which one is the faster reaction, which one is a slower reaction. And of course, whether they're endothermic and exothermic.